Hello, everybody. My name is Alan Rutenberg. I'm going to be hosting your webinar today. This is the definitive guide to the roll forming process. Now, our panelists are both with Rollform of Jamestown. Rollform has been doing roll forming since 1951. And our two panelists here are Pat Trinello and Mike Mattern. We'll start with Pat. Pat, are you there?
Yeah, well, thanks. It's great to be here.
Why don't you please tell us a little bit about yourself?
Sure. I started in industrial engineering in the late 60s. I've been doing, and that industrial engineering gets you involved nearly in every aspect of a manufacturing company. So for nearly 20 years, my industrial engineering background had me spending a lot of time on the shop floor analyzing typical metal fabrication operations. I now have about 45 years experience in the metal forming industry, with approximately 20 of those, I'd say, just dedicated to roll forming. As operations manager here at Rollform at Jamestown, it's been a great experience to look back and see just how much we've accomplished over the years. It's been a fun experience, and we're looking forward to passing on some of this information in our first ever webinar.
Great, thank you so much. And along with you is Mike Mattern. Mike.
Hi, Alan.
How are you doing today?
I'm doing great. And yourself?
I'm doing very well. Please introduce yourself.
Yeah, Mike Mattern. I'm the Director of Engineering here at Rollform at Jamestown. Don't have quite as many years in as Pat does, but I started in metal fabrication as a tool and die maker's apprentice back in the late 70s. And then since about 1983, I've been working in the roll forming field in a variety of capacities, probably around 20 years now in the engineering part of the job. So I spend the bulk of my day designing new tools, troubleshooting existing tools and processes, trying to make improvements along the way. So as Pat said, we're looking forward to sharing what we've learned along the way with the folks who've joined us on this webinar.
Terrific. Well, I'm going to introduce today's agenda, and then I'm going to let you guys take it away. The four things we're going to cover here is, first, we're going to do a basic introduction to roll forming, then talk about both the advantages and the disadvantages of roll forming, do a little comparison side by side between roll forming and break forming, and then this is my favorite part, we're going to get into guidelines to consider when you're actually designing your parts with roll forming in mind. And it all starts with an introduction to roll forming. At this point, I'm going to let Pat and Mike pretty much just take it away.
Yeah, what we say here is roll forming is a high-speed method of bending coiled metal, generally speaking, into a custom shape by passing the metal strip through a series of rollers. And what's shown on the schematic is a basic line, as I said. First off, we've got an uncoiler where the coil of material would be fed out and into the process. Typically, there is a press we call a pre-punch press, where we could punch features into the part, whether they're holes, notches, tabs, embossments, that sort of thing. And then from there, the material is fed into an entry guide to give the material a good, straight, square start into the rolls where the forming takes place. Next in the line is the roll forming mill itself. And we've drawn here schematically a mill with 16 passes. But quite honestly, there's anything from only a couple of passes up to 30 and more passes in some roll forming machines. This is where the forming of the actual profile takes place in the mill. Then at the exit end of the mill, there is a straightening device. And here's where we tweak the part a little bit. By this point, it's at its finished and final shape, but there may be some adjustments needed to compensate for a slight twist, camber, bow, etc. The next piece of equipment in a typical roll forming line, generally speaking, is a cutoff press, where we would cut off the part to length. There could also be a post-punching press between the mill and the cutoff press, but in this case we didn't draw it that way. The part is cut to length, and then it is put on a runoff table or a runoff bar, where it's made ready to either be packed into shipping containers to go out to the customer, or perhaps put onto a cart and moved to another place in the facility for additional secondary operations.
sorry to interject, but I just want to know, can you see the screen now?
No, we can't.
Okay, well, I just heard from one of our attendees that they can see the screen, so this might be something wrong with your screen. I will just say to our attendees, if you're having problems, please use your question box right now to let me know. But as far as I can tell, the screen is showing, and I'm told that people can see it just fine. So we'll continue.
All right, so let's go on from here. Let's go to the next slide, Alan, which will show a set of roll tools, roller dies. What you see here pictured is a model of a typical set of roll form tooling. You'll often hear roll formers speak of passes of tools, and that's how we refer to each set of top and bottom or male and female rolls. And if you count them here in this model, there are actually 6 passes. They're not shown in the mill, but they're showing as though they were set up in the mill. The light blue spindles indicating the machine shafts. At the top left, the stock from the uncoiler would enter into the mill. The first pass as a flat strip, and then progressively formed in each pass, going from pass 1 at the top left to pass 6 in this case to the bottom right, where you'll see the final channel shape, in this case a simple U-channel, exiting the last pass of the mill. Just a side note here, this is really just a representation of what you might expect to see. A light gauge U-channel or a light gauge part, short legs, very simple, might not even take 6 forming passes. On the other hand, you might require many more passes if the shape is complex or if it's a very deep channel. So just keep in mind, this is just representative of what roll tooling would look like set up in the mill. And Alan, let's go on to the next slide. What we want to do here is take a look at what would be representative of a single pass of roll form tooling. Now, let's focus on the section over at the upper left where it says there's a green outline there at the top of the rolls, T1, T2, T3, T4, representing the top roll or roll set. And then B1 through B4 in blue represents the bottom, which is the bottom set of that pass. So what we're showing here is like an end view or a cross-section view, something similar to what a tooling engineer would design for the building of these rolls, of course, without dimensions. And you'll notice that the rolls are segmented or split. Sometimes we call them slices. And we have really a couple of basic reasons for doing that. First of all, segmented rolls are much easier for manufacturing purposes. Rather than cutting the whole top or the whole bottom out of a single billet of some tool steel, we cut slices that are each closer to the finished size, so we waste less material. And being segmented, it's also easier for material or for handling for the operators. When they're going to put these in and out of a machine, the individual segments, of course, are lighter than if you had the whole top roll to put on the shaft as a single piece, and the bottom too, of course. The other reason that we segment these is because it gives us a chance to use these as a universal channel set. For instance, if you look over at the right-hand side of the same illustration, there are 2 spacers marked in red there. What that means is we could take the same tool set that's shown in the left, add some spacers, and use the same basic set of tools to make a wider channel. Also possible, you could change gauges many times in these same rolls because they're segmented, and you make the compensation for the various material thicknesses by use of shims and or spacers. So the universal channel approach is really good for a simple product like a U-channel. We also have universal angle dies, so you can have a variety of angles, different leg lengths on a simple 90-degree bend. And you can do similar things with hat channels, struts, Cs, that kind of thing. It really saves an awful lot of money for the customer because you can take advantage of an existing set of tools, and then perhaps rather than buying a full tool set, you can use our existing tools and just pay for a few spacers. Huge savings in tooling cost. The next slide, let's look at the next one. It shows the final operation in the line, and that is the cutoff press. we're looking at the exit end of a hydraulic cutoff press that we use on a line very similar to what we've indicated here in this schematic. It's a proprietary design, uses a servo-driven slugless cutoff. Basically, for an open shape, we can use a couple of steel plates that have a wire EDM through them that matches the profile with minimal clearance around it, so that when the die fires, the press fires, there's a shearing action that takes place, and it removes or cuts the length, the finished piece, from the roll form product, cuts it to length, and produces no slug, so there's no waste, and minimal burr, which is always a good thing. It's very intelligent, very efficient. The die sits at its home position until it's signaled by the controls to go out at line speed to the correct position, and then very accurately cut off the product to the correct length. And then it'll come back to the home position ready for its next cut. So think about how efficient that really makes it. Pardon me. Other than having to load coils or perhaps move loads of finished product out of the way, the operator really never has to shut the machine down. It's a continuous operation, flying cutoff, parts go on the load, and ready to just continue with his production. So that was a basic description of the introduction to roll forming, based around a very typical roll forming line. What we drew there in the schematic and the description we've given you certainly is not all inclusive. Not every roll forming line looks like what we've demonstrated here, but this is typical. You could have more presses either before the roll former or after. Some people have presses in the middle of the roll former. So there's almost an endless amount of variation in how the line can be set up. But this gives you, I think, a good idea of how the process works. So moving on here, then our next subject we want to cover is the advantages of roll forming. If you turn over to the next slide there, Alan.
Yep.
All right, so the paragraph says there that its advantages are speed. We can incorporate secondary operations in line. We can do very complex shapes as well as simple ones, and make extra long parts that you probably couldn't produce in a break. So then down along the bullet points there, holding tighter tolerances. Typically, roll form product, because we have so many opportunities to control dimensions in the tool set, we can control dimensions, cross-sectional dimensions, much more closely than other metal forming processes, for instance, a brake. When we're changing part lengths, it's really something that we can do on the fly. Quite often we can just put a new length into our controller for the line and go from 48-inch parts, let's say, to 60-inch length parts without moving a physical mechanical stop or anything like that. And because we're running a continuous production from coil and cutting it to length. Material handling and saving on floor space, they both kind of go hand in hand. If you think about the line that we just described, a coil of steel goes on the entry end of the mill. Operations take place in the pre-punch, perhaps forming through the mill, perhaps additional operations in a post-punch and or the cutoff. And out the end comes a part that is a net part, basically finished with all its features included, generally speaking. So we don't have blanks sitting around on skids or trucks. We don't have partially finished pieces that have had notches or a bend and waiting for the second bend. From start to finish, whatever amount of space that floor space that machine takes up and the load, and then the part is moved off to shipping or perhaps to a secondary operation. So we save floor space and handle much less product in our building. The last point there, which we've touched on earlier, standard shapes such as U-channels, angles, hats, and box or C-channels are often available with minimal or no tooling cost. And that's for the reasons we already described. Many times there are standard or universal channel and angle sets that will fit the bill for what you're looking for. So in those cases, maybe just spacers, maybe just some cutoff tooling, certainly a lot less expensive from a tooling standpoint, a brand new set of tools. Then on our next page, certainly, like any process, there are some disadvantages. And probably the single largest one with roll forming, it just doesn't lend itself very well to very small production quantities. When you think about what goes on here, you know, at times for very simple shapes, we can set up a machine in a few short hours. But more complex shapes, you may have a day or even 2 days at times into a setup. So if the production quantity is very small, all that setup time, along with any setup scrap that's generated to perfect the part during the setup, has to be amortized. All the cost that has to be amortized across a small production quantity, which can drive the per piece price up. The other thing that's a factor here is potentially higher tooling costs. For a custom shape, that could mean an entirely new set of tools, which could be expensive. On the other hand, many times when more conventional forming and fabricating methods are used, there are multiple dies and multiple tools that have to be built, and each one in its own press and each one in its own operation. Where with roll forming, we can quite often incorporate a number of features in our pre-punch operations, either by gagging, actuating features in and out of the die as needed. In some cases, we have multiple stations in a single die that are individually activated by hydraulic cylinders. So higher tooling costs, not strictly true, but at times it is. So that's one thing that would have to be taken into account. You have a comment?
Yes, when you were talking about the quantity, Mike, as far as roll forming, I'd say rule of thumb is about a mile or about 5,000 feet of product. If you have less than that, then you probably should look at conventional, your shear punch and bend operations. When you start to exceed the 5,000 foot level, then you should take a serious look at roll forming because it does become more economical. And of course, as your quantity, the amount of footage you run through the roll forming line goes up, your individual piece price goes down. At some point, it will level off, but you'll see a big difference between, say, 5,000 feet and 10,000 feet. But as you get to 15 and 20, your price will start to level off.
Yeah, that's a good point. And one way we've worked around that, and still do, you know, Pat mentioned 5,000 feet. Well, if your production requirements for any given time are, say, half of that, 2,500 feet, but you still feel that you'd like to take advantage of roll forming for whatever reason, what quite often we'll do is take a blanket order for future production requirements so that we can, on a single setup, perhaps run 2 releases for you. Even though each release to you may be half of what a good production volume would be, we could run it all at once, and that, you know, as long as we have an agreement and we know what the dates are, quite often we're able to work that sort of thing out. So don't let that be a showstopper. And of course, there are times certain products just can't be produced economically other than by roll forming. So the good thing is just let us take a look at it and see where we can help you with that. And we'll hold inventory when it makes sense. All right, let's go on to our next page. We've kind of talked about many of these things, but here's kind of a head-to-head, apples-to-apples summary of the pros and cons, roll forming versus conventional metal fabrication, which would include brake forming and all the shear punch, etc. As we said, roll forming typically wins out when it comes to tolerances. We just seem to have more control over the product than brake forming does, generally speaking. In the roll forming process, as we said, we can include inline punching, notching, eliminating secondary operations that other fabrication methods would have to use as a separate operation to include. Roll forming can produce complex and even very complex shapes, whereas more conventional forming is generally simpler shapes. Length of part itself, piece length. I've seen parts roll form for rail cars that are in excess of 80 feet long. That's not typical, but it's possible. You're probably never going to see that on a brake. Very often limited to the size of the brake, 10 or a 12-foot brake, perhaps a 20-footer at times. But roll forming, because it's a continuous forming process, we can cut it off to the length you require. And then the only factor that can that will impact that is material handling and trucking issues. But long parts are certainly an advantage of the roll forming process. High-speed production, once we turn the machine on, they run pretty fast, and you really gain some advantage there, especially versus the slower speed of a human being making each bend on a brake, along with all the other operations that go into that part. So what that does is result in lower labor costs per part for roll forming, which is an advantage there. One of the disadvantages we mentioned was potentially higher tooling costs for roll form versus potentially lower costs for brakes and conventional forming methods. But there are, as we said, ways that we can work with you on that. Universal tooling, shared tooling, things like that that can help make it more of an even eye-to-eye kind of a thing. Roll forming generally is a longer setup time. When you figure that the average roll form is 12 to 14 passes, you're going to have a fair amount of time setting it up and perfecting the setup before you're ready to turn on and make production. So in that case, typically conventional sheet metal fab might have a slightly better advantage there. Potentially more scrap with roll forming versus brake forming, etc. Again, amortizing it over a large volume of product makes a difference there. So that's only a potential difference. End flare, which is something we hadn't discussed up to this point, is pretty typical in roll form products. And basically what that is where the end of the channel, the end of the product being roll formed, will flare out, especially at the tail end of the part, sometimes at both ends. You typically don't see that in a brake form product. Roll form, you almost always see that. So at least on the surface, that appears to be an advantage to brake forming. However, there are cases where having some end flare in the roll form product is actually an advantage. We have some customers that use roll form products to stiffen vinyl, and having the end flare means when they put that stiffener inside it, it seats itself and stays in. It's not sliding in and out of the vinyl product. So they look at that as an advantage. We have some other customers that can't tolerate end flare. Well, we do what we can in the line to minimize it with some overbending, etc., special fixtures. And then we have some customers that just, it's like no end flare. Well, in that case, there are ways to deal with it as a secondary offline operation. We can deal with it. It's the kind of thing we should talk about. If you have products that are sensitive to that, then we need to know that up front. We'll certainly help you as much as we can to deal with end flare. That is a pretty good summary of what we've talked to so far, the pros and cons of the two processes, roll forming versus conventional metal fabrication. We're going to go on now to, Alan, to the next section here, guidelines to consider. These are some things that if you're designing a product and looking to have it roll formed, or perhaps you've got an existing product and you want to convert it to roll form to take advantage of the efficiencies of the process, reduce cost, these are some things you should take into account. Now, they really are only rules of thumb. They're only guidelines, not hard, fast rules. Pretty much everything that we're going to discuss over these next several pages, there are exceptions to them, and many exceptions. So all we're saying is take these things into account, and where you can design around these guidelines, you're going to be benefited when it comes to roll forming your product. So let's take a look at the first one. This is a wide panel. This is a wide panel, what you might think of as like a roofing panel, metal roofs. You see those quite frequently on residential and commercial buildings these days. I saw a metal roof on a building yesterday when I was out walking around the local community college. It's a metal roof, and what I saw when I looked up it was waviness, or oil canning it's commonly called, up the center of each of those metal panels. That's very common with white panels. You get much over 5 or 6 inches, and especially in the lighter gauge stuff, the center is going to wave. So what you try to do is, one suggestion here is add these longitudinal ribs, which we've illustrated in this cross-section drawing, that can help to minimize or at least disguise some of the waviness that's in the center of the part. Other products you might see that on here other than roofing panels, building panels, door panels, garage door panels, that kind of thing. Anything where you've got a wide web, light gauge especially, and you're doing forming only on the edges. So one way to compensate for that is with these longitudinal ribs, if that is an issue that you're concerned about.
And again, as you get into the heavier materials, that will not be as visible. The lighter gauge materials, say 20, 22 gauge, 24 gauge, 26 gauge, you're more apt to see some of that oil canning versus the heavier, say 14, 12, or 14 gauge.
Okay, that's right. That's Alan. Let's go over to our next page here. What we're showing is in this illustration is a J channel. It could be a cap for a molding or a panel. Quite often, all the forming on this type of product is done only on one edge of the stock, and the other side is left unformed. Depending on your use, if you may see the unformed edge get some waviness or some buckling to it. If we can add a safety edge, a little hem, or even a slight bend to that, it tends to take care of that waviness along that edge. Now, as I was starting to say, depending on your usage, maybe it matters, maybe it doesn't. If that unformed edge is hidden in the final installation or assembly, then perhaps it's nothing to worry about. J-channels are roll formed all the time. However, if it shows, then perhaps at least consider putting a slight form on the edge where, at least where we, in the bottom illustration there, we said not recommended. Well, we'd like to see you try something similar to either of the options shown up above there. Our next page, we're showing basically an end view, a cross section of a little box channel, and the arrows point into the bottom bends here. We'll call them blind bends. And what can happen is those bends, it's exaggerated here in this drawing, but they can actually become a little less crisp or softer bends than what are formed at the top of this part. There are ways to work around this. If we know that the bottom bends are critical and they need to be very crisp or square, there are things we can do in the tooling to make that happen. On the other hand, if it's not important to you, say this is just perhaps a stiffening product and it's hidden from view, maybe those larger radii don't matter in your particular use. If they do, though, be sure to call that out so that we can make some provision for that. All that happens there is at the point where the top bends cover the bottom bends so that you no longer have access with the male tool directly with the inside of the bends. They tend to round to get soft. Again, depends on your application whether this is a big deal to you or not. The prime thing here is just let the roll former know that that's going to be either something you care about or something that really doesn't affect the final use of your product. It's a good discussion to have. Let's move over to our next page, Alan. You'll see here a couple of different variations on a theme, closed channels. Now the top is a rectangular square tube with an open or a butt seam. And the lower one is basically just a variation of that, where we end up with two rectangular tubes at the extreme left and right of this roll form section. Now, when we looked at our slugless cutoff, the servo-controlled slugless cutoff earlier in this presentation, that's a nice open shape, and we can put a set of crop-off, shear, slugless, whatever you want to call it, plates can be put into use to cut those products off. This product, either one of these, would not lend itself to that because there's a hollow area that we can't get any tooling to support our cut. And what will typically happen is there will be some deformation from the cutoff, especially when the blade enters the part. Imagine a blade coming down into the seam of that top square channel, and it's going to deform the top until it starts to make the cut. And something similar with the bottom one there as well. The one at the top, we actually have a customer we make this product for all the time, and they're running or we're running for them 20-foot lengths, which they recut by saw so they can cut off the part that is damaged beyond their use. They just take that into account that there's going to be some of this product that they can't use because of the crushing of the end when it's cut. We have some other customers that actually use it the way it is. Again, it's a hidden part. It goes inside something else. Nobody sees at the end is crushed. It doesn't affect the function of it. That's just something to take into account. We can certainly cut off sections like this, but I just expect to see some deformation, a bit of collapse on the tube areas.
Oh, yeah, I was going to add, if there's a possibility of adding that gap, having that gap a little bit larger, that would be a lot better, because then we can get a mandrel in there and hold that and cut that off pretty square for you. So that's one thing to also think about in your design.
Yeah, we just, you know, each product has to be addressed individually as to the cutoff method being used. Just keep that in mind, and we'll certainly work with you on any designs you have where you think that maybe you can get away with it, maybe you can't. We'll be happy to give you some guidance. Cutoff is a big issue when it comes to roll forming, so we'd like to get in early and help you work through those issues in the design stage if at all possible. Our next page, here we see a nice open section, kind of the opposite of what we just talked about in the last shot. A nice deep U-channel, which certainly is a roll formable product. What you get into here as the section gets deeper, you also get into higher tooling cost. Imagine a wide strip of material that would be required to make this channel. If this is 6 inches deep and 2 inches wide, you're looking at approximately a 14-inch wide strip. Well, you've got to have roll tools that cover that and start the bends, and it takes more passes to finish these long legs than it would if the channel were shorter. So generally speaking, the deeper the product, the more expensive tooling gets. Sometimes you just don't really have a whole lot of choice. You need a deep channel, you need a deep channel. But many custom roll formers are not going to have necessarily a set of roll tools that will go indefinitely deep. Here at Roll Former Jamestown, we generally limit ours to 3.5, perhaps 4 inches because of the mills that we have here. So you're also limiting your options on what existing universal channel dies may be available. Now, all that said, can this be roll formed? Yes, and it is every day. Just deeper means more expensive from a tooling standpoint. Next page here, just some things to keep in mind when it comes to tolerancing your drawing. Like any fabrication process, roll forming works with coiled material or blanks in some cases, but we still have the material thickness tolerance to take into account. Typically what happens is roll forming forms the metal around the male tool, which is the inside of the part, and so inside dimensions are actually more consistent, whereas the material thickness variation shows up on the outside of the part. If you can, and it's practical, to dimension to the inside of your channel, you'll find that the variation is much less than measuring to the outside. Now, having said that, there are things we can do. If it's an outside dimension and that's really critical to you, we can put control passes in there to control, let's say, the width of this channel, regardless of the material thickness variation. We just need to know that up front and have the part toleranced appropriately so that the tools and the process meet your needs. Next page here. This is one that's pretty important when it comes to roll forming. Quite often you'll see a C-channel or a little box and some short returns, or ears as we often call them. There's kind of a limit there. If you can maintain a minimum of 3 times material thickness as the dimension for the straight segment of the ear, makes a formable part. If it goes less than that, it becomes very difficult to form, and especially as the material thickness increases. Just imagine that you're actually using, in effect, a lever to make that bend in the rolls, and there's just not enough to make the bend. It won't grab it and make it form crisply and evenly. Sometimes it'll even damage tooling if it's heavy gauge or high strength and that the bends are just too short. So here's the rule of thumb. 3 times material thickness as a minimum on the straight segment of any returns. Even if we can make it with bend with less than that, real hard on tools, it's going to shorten their life, and there'll be a great deal of tool maintenance and repair that runs into some money. So, and of course, as it wears, it's harder to maintain the integrity of the part. All right, next page, please, Alan. Here you should see a roll-formed part with a very large arc or radius. These are surprisingly difficult to control. Because the radius is so large, and especially in relationship to the material, it's really hard to get the bend, the arc, to set and stick. The arc tends to want to open up. I saw a job once where we formed it up very close to what's demonstrated here. When I exited the last pass, the whole thing opened up so it was nearly flat again. Can it be done? It can be, but quite often what you'll see is rather than one single large true radius or arc, it ends up being a series of shorter bends and lines, so it's almost like faceted. As opposed to being a true radius or a true arc, it's generally a series of shorter straight bends that will simulate an arc. So if it's high strength material, if it's something with a lot of spring to it, stainless, pretty tough to do. Just so much overforming required that it's very difficult to make that unless it ends up being faceted. Let's go on to our next page. This we're demonstrating a couple of narrow channels, and you'll see that it's called out there, they're both too narrow. Well, they are certainly producible. We produce some channels here that are much narrower than what's shown in this sketch. We make one product that's got a 5/16 opening on the inside with 11 gauge walls. The problem is not that you can't make the part. They are certainly roll formable, but it's very hard on tooling, both in tooling production. If you can imagine, it would have to be quite a narrow slice, a skinny slice of tooling that would have to go down inside these channels to maintain the opening while the part's being formed around it. Well, those tools are challenging when it comes to heat treating. They like to warp. They're that thin. They're also difficult as you get into the heavier gauges to keep from fracturing or cracking. We do have this one particular job that's what happens. We find that every few runs we have to replace some of those center slices because they fatigue and crack. There's a lot of side pressure, not much tool still there, and so they crack, and it just becomes a consumable part of our production run. We keep spares on hand. So very narrow channels, yes, it can be done. Just be aware that there are some tooling issues involved. And it will certainly work with you to work through whether the material gauge, the material properties, and the channel width is appropriate if they all fit together. Our next slide, actually the last one in this presentation as far as guidelines, we're showing here a kind of a short sample of a kind of a funny looking U-channel. Basically what we've done here is we've included in the sketch some features that might be typically seen in a roll form part that's most often pre-punched. The ob-round slot at the top right in the rear of the picture. There's a small round hole in the bottom of the web, very close to a bend. If you examine the right side of that same illustration, there's obviously a notch that goes around the bend. There's another notch that comes in from the edge of the stock partway down the side. And then between the two of them is a little embossment that sticks out the side of the part. All these things are quite common in roll form products. What we're recommending is, though, keep these features as much as possible away from the bend lines and away from the edges of the stock. It doesn't mean that they can't be there, but if they are, there's potentially some distortion to the feature itself. Perhaps the hole gets changed in shape as it goes through the roll forming tools. Even the the very cross-section of the part can be compromised just because there's just not enough strength in the places where you need strength, in the bends or along the edges where the material is flowing through the rolls. So we just want to try to minimize putting these features too close to the bends or the edges of the part. So as I said when we started this section, and I just want to reiterate, these are guidelines only, rules of thumb, not hard, fast rules. And to every rule, there's an exception. So just a good reminder, if you're considering a part, take these things into account when you're doing that. And we'll certainly be happy to share our expertise with anybody that thinks they can take advantage of it. That's all I have, Alan.
Thank you very much. I think it's pretty much time for our Q&A. So I'm going to put this screen up again. You may not have seen it before because of technical difficulties, but once again, the little red button should lead you to a control panel that looks sort of like this. If you're on a Mac or if you're on a mobile device, it might look a little bit different, but you should be able to find a question box. And I'm going to give everybody a few moments to write in questions if they have any. I see a couple people have already written in. I'll tell you what, while people are writing in, why don't you tell me, Mike, Pat, are there any very big takeaways you think from this presentation? Anything that you definitely want people to remember?
Well, first off, I was pleased that there was such a large number of attendees, and it's nice to see that people are interested in learning more about the roll forming process and the possibilities of reducing their piece part costs by utilizing this process. You know, as we all know, in today's engineering world, it's all about reducing costs and utilizing more efficient manufacturing methods. And you really can do just that by taking a hard look at roll forming versus conventional conventional fabrication, I'm sorry.
Okay. Well, let me ask a few questions here that are coming in. I have a question from Sam, who basically he wants to know what types of materials can be roll formed.
Yeah, that's a good question. That's one we get quite frequently. What we typically tell people is any material that you can buy in coil form can be roll formed. Carbon steel, whether it's cold rolled, hot rolled, HRPO, stainless, mostly all the stainless alloys, aluminum, red metals, brass, bronze, copper, galvanized, pre-galvanized, pre-painted, pre-polished. Pretty much anything can be roll formed. There are some exotic things that probably cannot, but generally speaking, anything that's typically used in more conventional forming methods can also be roll formed.
Someone wants to know, what are the material thickness limitations?
The material thickness limitations, generally that's a function of the size of the mill. Roll form machines come in a variety of sizes. Most of your roll formers are going to have what we often refer to as an 1.5-inch mill. It's an 1.5-inch spindle, or a 2-inch mill with a 2.5-inch diameter spindle. The spindle diameters will play a huge part in controlling or allowing for material thickness. Obviously, you have to have enough stiffness in the spindles and the bearings and the housings, etc., to handle the maximum material thickness. Generally speaking, and I think most roll formers will tell you the same thing, 15 thousandths on the low end for thickness, and generally around 11 gauge and 1/8 of an inch or so thick on the high end. And of course, there are exceptions to this too. There are roll formers that produce material, or roll form material that's probably 5/8 of an inch thick, but that's not typical. That's more the exception. Typically, I'd say 020 to 125 is the general most popular range.
Brad wants to know, do the segments leave significant marking on the finished parts when designed this way?
No, they do not. What you don't see in that cross-sectional drawing that we had there on that slide, you usually put a small radius where those, there may be a slight misalignment, lack of concentricity of a few tenths to a thousandths, going from one roll segment to another. And so what we do is we put a little tapered radius on the corner of each where they meet, so that you don't have a sharp edge that's making a mark on the material. The other thing we try to do as much as possible is locate the splits in the rolls where the bends are going to be, so that if it does make a mark, they disappear in the bend, or they never even show up on the bend. If the finish is critical, then that's something obviously we'd want to know going into it, so we don't use a set of tools that would make marks. We have some old tools here, we have some brand new tools here. The new ones are more precise than the old ones, just because of the manufacturing process. But we can avoid making marks because of the roll splits, yes.
Okay, I'm not sure if this is a question or a comment, but I'll pass it along. The design guidelines with 3 times thickness for flange, dimensioning without gauge thickness would apply with all sheet metal, I would think.
Probably so. Yeah, I can't argue with that. I'm speaking from roll forming, but I think that probably is generally true for any process.
Okay. This is a nice question. What determines how many forming passes are required?
Well, there are a lot of things, a lot of factors that play into that. Obviously, the complexity of the shape. The more bends, the further the metal has to be bent to make a formed product. That will impact how many passes are required. Tolerances of the part. The tolerances of the part, more passes allow more control over dimensions of the cross section. Deeper sections, like we talked about that deep U channel, more passes. So deeper, the more passes. Material thickness, material properties such as high strength, pre-finished materials, whether it's pre-polished or pre-painted, parts that have pre-punched features in them. All those things can impact the number of passes as well as line speed. The mill itself, that's the other thing we talked about, what the size of the mill is. It's commonly referred to as 1.5-2 inch mills. Well, each of those mills has a space from pass to pass, or forming station to forming station. So all that has to be taken into account too. How much forming you can do between each pass is sometimes a function of the mill. One thing we didn't talk about much was pre-cut blanks. We don't happen to do that here. It's not that we have never done it. There are some roll formers, quite a few of them, that will run pre-cut blanks as opposed to coil. I don't think it's as efficient a method, but you also do need more passes when you're running blanks through a mill versus coil for the same or similar product.
Okay. If you are roll forming a soft material such as aluminum and the surface is critical, how complex is it to keep the tooling clean, and is bare metal finish always a problem?
Can I have the question one more time, Alan? I just want to make sure I understand it.
Sure. If you are roll forming a soft material such as aluminum and the surface is critical, how complex is it to keep the tooling clean? Is bare metal finish always a problem?
Bare metal finish is not always a problem. Aluminum has its own set of special considerations. I'm not an aluminum roll forming expert, I'll be honest with you. I know it does tend to have a little almost stickiness property to it and build up on the rolls. And so what that means is more roll maintenance, more cleaning. I really don't know how to answer the surface critical part of that question when it comes to aluminum. I apologize, but that's just outside of my experience.
Okay, and that was a question from Paul, and so I'll just say, Paul, if you want to write in with a clarification on that question, feel free. Maybe we'll get back to it.
Yeah, that's a good idea.
Okay, how about this one? Well, this is about line speed. So what is typical line speed? Okay, and how much product can a roll former produce in an hour is the follow-up question to that.
All right, that's a good question. I'll mention typically what you'll see and then mention some exceptions. Typically, you're going to see anywhere from 20 or 30 up to 100 feet per minute gross line speed when the product's actually running. There are some specialized mills that run several hundred feet per minute, stud and track, some tube and pipe people. But generally speaking, most roll form product runs in that range, 20 to 30 on the low end, and that's usually the case if you're running a complex pre-punch pattern or anything else that needs time to recover, or very short pieces. 100 feet per minute, you're going to see that if you're running generally long lengths, generous length tolerances, and a lot of product. If you have to have, for instance, that little cross section we showed, I think it was our last slide, that had a hole in the web, if that hole were to be pre-punched, which odds are would be, and then that hole had to be registered an exact distance from the end when it cuts off, that's also a determining factor for line speed. Now, what I've been talking about so far is like gross line speed. That machine's running at 100 feet per minute. So when it's running, it's producing 100 feet of product per minute. But obviously, as there are adjustments that need to be made, coils put up as one runs out, loads moved, things like that. So your net line speed is going to be significantly lower than the gross line speed. The other thing is heavier material. When you put up heavier coils, those coils have fewer feet of product in the coil. So you run out the material and then you have to either feed or weld on an additional coil. So thicker product also will impact line speed and your net.
Well, you know what, I'll tell you what, the next question then comes from me. I'm curious, has it changed much over the years? I mean, we mentioned before that Rollform has been doing this since, I think, 1951. I mean, we don't necessarily have to go back that far, but has the line speed increased significantly over the years? Has it become more efficient in that way?
I'm not so sure the line speed itself has been the big improvement. I think it's probably controls. Years ago, when I first started, I remember everything had a mechanical trigger where you had to pick up on a punched hole or feature in the part, and everything was pulled back with door springs and to get to the home position for the die. A lot of mechanical stuff going on that you just couldn't speed up, and so consequently back in those days you ran a slower line speed and you produced a lot more scrap. Today the controls on the machines, including the presses, are so much more sophisticated that you can put more features in the product in line. So that helps line speed, not only the gross line speed, but also the throughput, because you imagine now instead of a channel coming off the end that you need to take over to a punch press as a secondary operation to punch holes in it, now you can run that same channel and the holes are already in there. So it's, you are gaining huge efficiencies, which may not necessarily be the result of only, gross line speed changes.
Okay. We'll probably have time for just maybe one or two more questions. I'll tell the audience, if you have questions, here's your last chance to get them in. And if we don't have time to answer them right now on this webinar, we can get back to you just by email and answer your questions. We're happy to continue dialogue that way. But I'll just give one or two more questions. What is the material thickness that can be roll formed? Did we already
yeah, we covered that. Yeah, we covered that.
Then let me go into this one. What industries typically use roll form components? Yeah, so what industries have you seen?
Oh boy, which ones don't? It's probably the easier question. Yeah, any formed metal part. One that probably most people are going to be familiar with is gutters, gutters on their houses, aluminum. But the bigger ones, other building products. The metal roofing is a huge industry right now. Siding, trim, exit devices, the ceiling grids that you see in your suspended ceiling are roll formed. Tons of stuff in the truck, trailer, automotive industries. Racking, shelving, imagine all those beams and posts and racking systems are roll formed. Store fixtures, store displays, guardrails is another common product. There's office furniture, office partitions, drawer slides, cabinet parts, office furniture parts, struts, cable trays, that's another big one. The appliance industry, the automotive industry, they're just everywhere. It's almost, and then of course that doesn't even touch the tube and pipe, which is basically the same process, but it's making a welded seam product that goes into bike frames, golf clubs, you know, every piece of tube and piping that you see. Roll forming is huge.
Okay, well that's probably a great note to end on because we're just about out of time. So I want to let everyone know that I'll be sending by email a very brief survey to all attendees. We'd love to get feedback on the presentation. And I'll tell you that if you asked a question that did not get answered yet, and there are quite a few of you who did ask questions that we didn't have time to get to, once again, we will get back to you. We'll be happy to answer those questions over email. With that, I'm going to say thank you, Mike, and thank you, Pat. You guys were both great. And thank you to the audience, to everyone who attended.
Okay. Thanks, Alan. Thanks everybody.
Alan.
All right. Take care, everybody.
Yeah. Bye now.